Now we will move into a discussion of how we graph functions on the XY plane. We will talk about the very basics of graphing functions on the XY plane. We will also talk about some important features of graphs when they are on the XY plane. And the first few items that we talk about in section 16.2 are really going to reiterate some of what we just went over in section 16.1, the function basics stuff. But obviously what we will add here is a bunch of notes that relate function notation to points on a function's graph. So again, this should just be a little bit of a review here, parts of a function's definition and the relation to points on the function's graph. So we have, again, the function name. Remember that we have in parentheses over here on the left-hand side of the equal sign, we have our input or our x value. That's the item, the value, the variable that will go into the function. And then remember that on the right-hand side, I'm going to jump to number 3 here. That is our output. It is our y value when we graph functions on the xy plane. We can also call this our f of x value. We can also call it the value of the function. And do keep in mind, I'm just going to jump back to number 2 over here, that this is an equal sign. So everything on the left equals everything on the right. So when we see something like f of x equals 2x plus 3, again, there's our input over there. And then everything over here obviously is f of x. And that means that everything over here is f of x because the two sides are equal to each other. So again, in position 1, I'm going to highlight some stuff here. We have our input. It is an x value. That is the thing that is substituted into the function anywhere we see the input on the right-hand side of the equal sign. And we plot that value on the horizontal, or obviously on the x-axis. That is our x. We plot that value that's in parentheses on the x-axis when we are plotting points of a function on the xy plane. In positions 2 and 3, the entire left side and the entire right side of the equal sign, we have the output f of x or y value. We already wrote that up here. That is the result that we get when we substitute our input into the function. And we can also call this the value of the function. You will see on the SAT that language. They will say something like, what is the value of the function when x equals 2? They are simply asking you what the y value is, or what the result is, or what the output value is. And of course, as I just mentioned, we do plot the value of the function on the y-axis. Our y coordinate represents the value of the function at a particular x value. One other thing that College Board has been very fond of doing lately, it is actually not all that difficult to understand if you are really familiar with functions and how functions relate to the xy plane, but for students that are even a little bit shaky on that, these questions actually can be a little bit difficult mainly because of some of the notation involved and understanding that notation. So what we're going to do is we're going to run through 6 ways that we can reference point A on this linear function. So we have this linear function f of x equals 1.5x plus 2. Remember that we are graphing as the y coordinates. As the y coordinates, we are graphing the values of f of x. So if a certain value of x goes in, like let's say x equals -3, then we would do 1.5 times, I chose an ugly value there. Let's do -4. We would do 1.5 times -4 plus the 2, 1.5. That's not supposed to be a 0.4. That's supposed to be a -4. 1.5 times -4. What is that? -6. -6 plus 2 equals. So that's -4. Wow, -4, -4. Is that right? I'm going to check it in my calculator here just to make sure I didn't make any careless mistakes. So -4 times 1.5. And yes, I did get that right. Good. Obviously, if I had been on the no calculator section there, I would not have used my calculator. I would have just trusted myself. But anyway, when -4 goes in, -4 comes out. So again, we plot the x value in parentheses as the x coordinate on the xy plane, and we plot the output or result as the y value. They happen to be equal to each other here, so this would be the point, -4, -4. So again, in terms of point A, there are two generic representations for any point on any function on the xy plane, and that is, the first one is one we all know and love. That's just the regular old x, y. But remember that because we are plotting functions values on the xy plane as the y coordinate, we could also call any point on the xy plane or on a graph on the xy plane x comma f of x, because again, y equals f of x. So y equals f of x, so I could just write f of x in the y position. So those are the two generic representations. Again, any function, assuming the function is named f, could be written as x comma y or x comma f of x. If the function were named g, then we might have something like x comma g of x. So again, these are not only generic representations, they're also representations using variables or symbols. We'll talk about some representations using numbers and symbols in a moment. The third representation using variables or symbols is we could write point A as x comma 1.5x plus 2. So remember, we just said that y and f of x are equal to each other. You can see that right there. We're plotting f of x as the y values. Well, remember, f of x is also equal to 1.5x plus 2. In other words, any point along this line, we are going to have an x value, and then we are going to have a y value that is equal to 1.5x plus 2. So we could express our y values in terms of x as 1.5x plus 2. And I've said this before, I'll say it again. We can also write this equation as y equals 1.5x plus 2, because once again, for about the sixth time, y and f of x are being represented as being equal here. In D through F, now we're going to use some numbers and symbols. And again, another very concrete way that we can refer to point A is 2 comma 5. Our x coordinate is 2. Remember that x coordinate means that we are going out from the origin or out horizontally from the y-axis. We're going out 2 units. And then the 5 means we are going up 5 units from the origin or 5 units from the x-axis. So again, the x value represents the distance to the right or left of the y-axis, and the y value, the y coordinate, represents the distance above or below the x-axis. So y is relative to the x-axis and x is relative to the y-axis. So that point obviously could be 2, 5. This point could be 0, 2, and so on and so forth. In terms of another way that we could represent this point, we could call it 2 comma f of 2. Because remember that the y value at this point is whatever f of 2 is, and of course f of 2 is 1.5 times 2 plus 2, that's 3 plus 2, that equals 5, and that makes sense because the y value right there is 5. So we could refer to that point as 2 comma f of 2 in the same way that we can refer generically to any point on any graph as x comma f of x. We can refer to this as 2 f of 2, where 2 is the x value and f of 2 is the y value. And then last but not least, I think probably the one that most students are sort of most unfamiliar with. This doesn't look at all like a point, but remember that if you are given something like f of 2 equals 5 on the test, I'm going to write this down over here, f of 2 equals 5. We've said this many times already. That right there, that 2 in parentheses, that's an x or an input value, and we have said that both of these sides are y or output values, so that 5 right there is an output value. So when you see something like f of 2 equals 5, you need to understand that what that means is that you're talking about the point 2 comma 5, x value, y value. You also may have the opportunity to substitute, because remember, if you're given a 2 and a 5, and then elsewhere you're given an equation or a function, you may be able to take that 2 and throw that value into the function for the x. So for instance, let's say we had, I don't know, f of, well, even this guy right here. Let's say we had f of x equals 1.5x, but let's say they didn't give us that 2. Let's say they said plus b, and we needed to know the value of b. Well, if they also tell us that f of 2 equals 5, that means that 2 could go in for x, and that 5 could go in for f of x, the entire left-hand side of the function here. And what we would end up with is 5 equals 1.5 times 2 plus b. This would be 5 equals 3 plus b, I'm running out of room here, minus 3, and we would get 2 equals b, and we would be able to solve for that b value. So again, when you see something like f of 2 equals 5, or even something like 2 comma 5, you just need to keep in mind that there is a possibility that substitution 2 for x, 5 for y might be valuable to you. Do want to say one other thing. I probably should have said this when we were talking about function basics. Most students understand this, but I do feel the need to say it because I've seen students make this mistake before. I'm going to write this down over here. Note, f of x, it is a single entity. It cannot be divided by f or x. In other words, you can't get rid of that f by dividing by f. You can't get rid of that x by dividing by x. F of x this is not multiplication. We are not multiplying the f and the x. This is function notation. And when we see function notation, we need to understand that f of x is indivisible. I cannot divide f of x by an f or by an x. Now, of course, if I had f of x equals 5 and I, for some reason, wanted to divide I don't know, by 2 or 3 or whatever, then I can do the division. But f and x are not individual variables that can be canceled out through division. Keep that in mind. Again, most students already know that. At the top of the next page, we're going to do a few examples on this page. Let me get up here. We said many times in the previous section of section 16 here of the function section that a lot of these questions are about substitution. I just gave you an example of a question where you could substitute. Example 8 is actually going to be very similar to what I just did on the previous page in solving for that b value. If you understood what I did in that previous example, you should be fine on example 8, which means you can go ahead and pause the video and do this on your own. We can use the calculator on this question. I don't believe we're going to need to. However, again, pause the video, do example 8 on your own, and then join us. In the xy plane, the point 2, 1 lies on the graph of the function f. If f of x equals k minus 3x squared, what is the value of k? That's what they want here. So again, remember, as soon as we see functions combined with points in a question, we should immediately be thinking, okay, well, when it comes to the function, that 2 is an x value, and that's not specific to functions, actually. That's just specific to xy coordinate plane notation. And that 1 is a y or f of x value. And what that means is I can now substitute the 1 for f of x and the 2 for my x. So I get 1 equals k minus 3 times 2 squared. And now this is a very simple basic equation. 2 squared is 4, negative 3 times 4, so that's minus 12. I'm going to add the 12 to both sides. I'm writing down my intermediate steps. I get k equals 13. Let's make sure that's what they were asking. Yes, it is. They wanted k, so I am done here. Again, very important to remember that when you are given a point, you on the xy coordinate plane, you have an x value, you have a y value. So if elsewhere in the question you have a function with an f of x / y and an x in it, you may want to substitute. We will take now a look at an example where we have a graph, and in fact we will not be given the function at all, and that's fine. The function's actually sometimes irrelevant when we have a graph. There are a bunch of examples here, some of which are going to be exceedingly simple and others that are going to be quite hard even for some students that are extremely familiar with functions. I would probably pause the video and try to do as many of these on your own as possible. Once you have done whichever ones you think you can do confidently, come back and join us and check your answers and watch me go over any that you were unsure of. So on example 9, for linear function f, okay, so they label the linear function. I'm going to actually, just to make this stand out a little bit more, so that's f, and quadratic function g, so that's g. In fact, let me do that over here too. I don't want to have to worry about forgetting which is which. Is graphed in the xy plane. By the way, the way that you would know which is linear and which is quadratic is you would know information from previous sections, section 8 and section 12 in this manual. Remember that linear functions are lines and quadratic functions are parabolas. So there should be no question that the u-shaped curve here is the g function, and the straight line is the f function, the linear function. Determine the following. Okay, so we've just got a bunch of stuff to determine. We need f of 1 minus g of 3. Okay, so again, this all goes back to everything we've talked about so far. What is an input? What is an output? What is an x? What is a y? Those two values there, the 1 and the 3, are obviously x values because they are in parentheses after the function letter name. So f of 1 simply means that we need to go along the f function to where x equals 1, and we need to find out what the output or y coordinate, the y value, is at x equals 1. So if I go to 1, there's the x equals 1 right there, and I just travel down to the linear function, I can see that f of 1 is going to equal negative 2. So my y value at that point is going to be negative 2, which means that f of 1 equals negative 2. Now for the g function, we are being told we need to evaluate that function at an x value of 3. So I go 1, 2, 3. There, nope, see, that's what I didn't want to do. That's the f function. There's the g function. That's 1, 2, that's negative 3. So the y value there is negative 3, which means that f g of negative 3, I am messing all of this up. That means that g of 3, see, even I'm confusing my inputs and outputs, is negative 3. So what we now have to do is f of 1, which is negative 2, minus g of 3, which is negative 3, negative 2, minus, I'm going to use some parentheses here so I don't mess this up. That's going to be negative 2 plus 3, which means we are talking about a value of 1 here. So again, the 1 and the 3 are input or x values. We need to evaluate each of these functions at those x values, find out what comes out of the function or what the y value is, and then this just becomes a simple arithmetic question. B's, 9b here. So if g of 1 equals p, what is the value of f of negative p? Okay, so in this case, again, we have an input value that's an x equals 1. So we need to go to the g function where x equals 1 here. So I'm going to go down to the g function at that point. So what is that? 1, 2, 3, 4. So that's negative 4. So g of 1 is that y value. That's g of 1. That equals negative 4. And that's the p value. They say g of 1 equals p. We just found that g of 1 equals negative 4. So that's the p value. P equals negative 4. They are asking us for f of negative p, f of negative 4, which is f of 4. So again, now we have a input for the f function. That is an x value of 4, 1, 2, 3, 4. And there's the f function when x equals 4, and that looks like it's probably about, negative 0.5, let's say. We're supposed to round to the nearest tenth. Yeah, that looks good. Negative 0.5 is the value of f of negative p. In the next example, we have f of a equals negative 1. What is the value of negative g of a? Okay, so in this case, you notice that we are given not an x value. Okay, here we're given x, x, x. Here we are given an output or y value. So we have to sort of work backward to find out, and we did do this in the previous section. We have to work backwards to find out what input value, in this case an a value, produced that output value. So remember that a is an x value, and that negative 1 is a y value. So we need to go on the f function, the linear function, the f function, to where y equals negative 1, and that point is right here, right? This is y equals negative 1, so I'm just traveling over to the f function. So that is the point where y, the output, equals negative 1, and the input that produced that output is 1, 2, x equals 3. So that means our a value must have been 3. When a or x, the input, is 3, we get an output of negative 1. So now all I have to do is negative g of 3, negative g of 3, because 3 is my a value. And now what does that mean? That means that this 3 is an x coordinate on the g function. So I'm going to go to where x equals 3. 1, 2, 3. It's getting a little messy up here. And we're talking about this point here, which I believe we've dealt with already. That's why there's a point there. And that point is 3 comma negative 3. So the output there is negative 3. So I've got to be careful here. I'm going to do that. We've got negative g of 3, we just found g of 3 to be -3. So we're talking about -3, which equals +3. You got to be really careful with the negatives. A lot of room for careless mistakes there. In example 9D, we have f of m equals g of m, and m is less than 0. What is the value of m? Okay, so remember that all this is saying here is one really easy way to think about this. When they talk about f of m, obviously the m, both of those are x values. They're the same x values because the m's have to be equal to each other. So what f of m is it's simply a y value on the f function, and the g of m is a y value on the g function. So they're telling us that we need to look for a point where the y value on both f and g are equal, which means we're talking about points of intersection. That's what we're talking about. And there's 2 points of intersection. There's one here and there's one here. So what that means is that this point over here is going to be what? I might have to erase this later to clean this up a little bit, but that's -1, -3. And this point over here is 1, 2, 3, 4, 5, comma 0. So what's going on here is the y values at this point are equal. They're both -3. The y values at this point are both equal. They're 0. So the x values need to be either, and again, our x is an m here. So that m value either needs to be -1 or 5. Those are the two. So I'm going to write m equals -1 or 5. But the question tells us that m is less than 0. So it's got to be that -1 that's the relevant value of m. M must be -1. When m is -1, that means our x value is -1, and our y values would be -3 on both functions, and -3 would indeed equal -3. In example E here, for how many values of x does g of x equal 2? So how many, they're asking us how many values of x will we get a g of x value of 2? Again, we could think of this as a y value on the g function. I'm writing a little bit small here because I want to keep this graph on the screen while I do these examples. So my apologies if this is getting hard to see. So the y value on the g function equals 2. Well, remember, when we want to find out where a y value equals 2, we've got to think of, so I'm going to actually write this down. When we have an equation in the form y equals b, some number, okay, some number, some constant, we've got to remember that that is a horizontal line. And this is reviewed in, I believe, section maybe 8, graphing linear equations. Anything in the form y equals b is a horizontal line. Anything in the form x equals c, again, where c is some number, that is a vertical line. Vertical line. So in this case, we've got y equals 2. So what I'm going to do just to help visualize this is I'm going to draw a little dotted line where y equals 2, right? That's a y value of 2. So y equals 2 represents all of the points along that horizontal line where all of the y coordinates are 2. And we should be able to see that the g function hits that line or intersects that line at 2 points, which means there's 2 points on the g function where the y value equals 2, which means that there are 2 x values. That's what the question's asking us. How many values of x will produce a y value on the g function of 2? And we can see that it's 1 and 2 points, which means there are 2 values of x. It's not important to know what those values are. We could find them, -4 and 5 or 6, something like that. But the question's not asking us what those values of x are. It's just asking us how many of those x values are there. In example 9F, we have a composite function. We did talk about these in a previous part of the function section. So g of 1. So we talked about the fact that we should do inside function first. So I'm going to do g of 1 first. And of course, g of 1 is -4. We've done that before. And now that -4 can be substituted in for the g of 1 in these parentheses, which means we are now evaluating that outer g function. And we're evaluating that function at an x value of -4. So again, the 1 is an x value for the inner g function. So we evaluate that inner g function at x equals 1. We get -4. Now that we have that g of 1 equals -4, that -4 becomes the input of the outer g function. And now I need to find out what g of -4 is. And g of -4, 1, 2, 3, 4 is that. It's that point we were just talking about. It is going to be 2. G of 4 equals 2. When x goes into the g function, a 2 comes out for the the y or the value of the function, which means that g of 1 is 2. In terms of the next example, yeah, it's going to get hard to keep this all on the screen here without getting real small. We've got another composite function, this one involving both the g and f function. So we have got g of f of negative 2. I'm going to write this in what I feel is sort of the more, intuitive way. G of f of negative 2, that's what this notation means. So f of negative 2, let's do that as quickly as possible. F of negative 2 means we go to where x equals negative 2. We find the value on the linear function, the f function. So 1, 2, that's negative 2, and then 1, 2, 3. It looks like negative 3.5. So f of negative 2 equals negative 3.5. So now I am doing g of that negative 3.5 value. So I go to where x equals, remember that's an x value. I go to where x equals negative 3.5. 1, 2, 3. So 3.5 is about, I don't know, there. Well, that works out nicely. So it looks like on the g function, when x equals negative 3.5, my y value is 1, which means that g of negative 3.5 is 1. So that is the answer to that one. In H, g of x is greater than f of x. What is one possible value of x? So again, all this means is that the y value on the g function needs to be greater than the y value on the f function. And I think the easiest way to do this is just to look for places on the graph where the g function, the parabola, is higher than the f function. So for instance, like at g is above f here, that point, I believe we were just around this point, we can see that 1, 2, 3, negative 4. At negative 4, at an x value of negative 4, the y value on the g function is greater than the y value on the f function. So there's the y value on the g. There's the y value on the f. So that's one possible value of x. We could do 4. And in fact, anything to the left of, I'm going to shade this and then I'm going to erase it. You can see that anything to the left of that point where the two functions meet, you're going to have an entire region here where the g function is above or greater than the f function for any given value of x, which means that any value of x that is less than the value of x at that point of intersection, which is negative 1, any value, actually not equal to, sorry, less than negative 1. X just has to be less than negative 1, and we will have a value of x that satisfies g of x is greater than f of x. Whenever x is less than 1, the g function will be above or greater than the f function. In example I here, what is one possible value of x for which the product of f and g is negative? So in this case, probably, what's the easiest thing to do here? Probably, let me get rid of this green. This is getting very crazy up here. Probably to look for an x value where one of these is positive and the other is negative. So for instance, if I'm considering, I'm going to zoom in here for a moment. If I'm considering an x value of, let's say, 2, okay? Well, both the f function and the g function are negative there, which means that when x equals 2, the product of those two functions is going to be positive because I will have a negative and a negative multiplied together, which will give me a positive. But when x is, let's say, negative 4, let's go back to that point over there. We can see that the g function is positive, right? The value of the g function there is positive 2. The f value, the f function is negative. It's negative, I don't know, 4.5, something like that. So when I multiply the value of the g function by the value of the f function at an x value of negative 4, I will indeed get a negative number. So there you go. That's one value of x. One value of x that will make the product of the f and g function negative is 4. And if you want a range here, let's see. So the g function turns positive there. So anywhere to the left of negative 3, the g function will be x equals negative 3. Anywhere to the left of that point, the g function will be positive, the f function will be negative, which means that any x value, x is less than -3. Any x value less than, this was supposed to be -4. I apologize for that. Sorry, that should have been -4. At an x value of -4, the f function will be negative and the g function will be positive, which means that negative times positive is negative. Any x value to the left of -3 would have worked on that question. Here's where we get some very tough questions. So J here, if f of a, absolute value, that's absolute value of f of a, equals g of a, and if f of a does not equal g of a, what must be the value of a? So we are looking for an x value, those a's are x values, that makes the absolute value of the linear function, the f function, equal the g function, but we can't consider a point where the two functions are equal. In other words, this means that we can't consider, I'm going to write this down, no points of intersection. They can't be intersecting. That's what f of a equals g of a would mean, that they intersect. If f of a can't equal g of a, we can't be looking at a point of intersection. So what I'm going to do here, absolute value of one equals the other. I guess I could spend a couple of seconds trying to figure out exactly what that would mean in terms of which region of the graph I should look at, but I actually think the easier way to do this is a little bit more direct. I can see at that point right there, so what is that? That's an x value of 1, 2, 3, 4, -5. At x equals -5, the g function equals 1, 2, 3, 4, 5, and the f function equals 1, 2, 3, 4, -5. So let me jot this down. So when x, I'm going to write this over here. When x equals -5, the f of x function equals -5, right? That was that point right there. That's 1, 2, 3, 4, -5. 1, 2, 3, 4, -5. And the g function was -5, 5. So let me write that down. G of -5 equals 5. Well, look, the absolute value of the f function, if I absolute value that f of -5 equals 5, absolute value of f of -5 is going to equal positive 5, and then those two are going to equal each other. So it is at that -5 value that the absolute value of the f function equals the g function, which means that a, which again is an x value, must be -5. A must equal -5, and if it does, then absolute value of the f function at that point will equal the g function at that point. In item K here, if g of n is less than h of n is less than f of n, then n comma h of n could be which labeled point. Okay, so again, first let's just let's circle that. Could be which labeled point. Let's just reiterate the fact that this is just one of the ways that we can express a point on the xy plane. That n is an x value, and know that because it's in parentheses after the letter name of this function, and that h of n, that is a y value. So they're just giving us a point here. N comma h of n is just a point. That's what they ask us. N comma h of n could be which labeled point. So we need a point where the y value is between the y value of the g function and the y value on the f function, which means that the f function has to be above the g function. So let's look in this case at the sort of intervals here, or the sections of this graph here. Here the g function is above the x function, so that's you know what, I'm going to do this in a different color so it's easier to see. So at this point they meet, and to the left of that point g is above f, and then over here they meet again. So from that first vertical line that I drew to this second one, the f function actually is above the g function, right? For any x value here, let's say, I don't know, this x value, right? The y value on the f function is above the y value on the g function. So it is the case that in this interval, from that first vertical line to that second vertical line, the f function is always, for any x value, going to be above the g function. And that's what we wanted. We wanted the f function here to be above, greater than the g function, and the h function would have to be between those two lines, and it looks like that would mean that the h function could be on C, wherever the h function is. I don't know where it is. I mean, it could be, you know, an upside down parabola. It could be another line. But whatever the h function is, it could be the case that point C could be on that h function, because point C is greater than the g function. It is greater than the g function, but less than the f function, the y coordinate at point C. So I'm going to put point C. That could be the labeled point. Bunch of examples there. If you understood those, then you are well on your way to pretty much acing all of the function graph questions. I shouldn't say all of them. A lot of the function graph questions that resemble these kinds of examples on the test. At the top of the next page, we're going to throw a table into the mix. And we should keep in mind that the table doesn't really do anything different. Remember that a table of values, for instance, with this h function, we have our inputs, our x's, and we have our outputs, our h of x's. Remember, this is just an xy table, so we're just being given more points. That's all that table represents. Again, if you're feeling very confident with this, we've got a bunch of examples here. I would work through them as quickly as humanly possible, and then if you, again, are feeling confident, just race through my answers to make sure that you got all of yours right and that you know how to do them. If you are not confident with this, then I'm going to work through it right now and you can watch me. So relating function notation to points on function graphs and in tables. So again, we have the same two functions here. We have that quadratic function g, we have that linear function f, and now we have this new function h, but h is not given on the graph. We don't have the curve or graph of h. We have a table of values for h, and we just need to determine the following. So this notation right here, f plus g plus h of 4. First of all, there's this little note box over here that you might want to take a look at. There are a couple of different types of notation that might pop up on the test. We already talked about composite notation, f, fog, and goff. And that now we have some other notation that revolves around adding, subtracting, multiplying, dividing functions. So when we see something like f plus g plus h of 4, all that means is f of 4 plus g of 4 plus g of 4 plus h of 4. In other words, we're just adding the values of each of these functions when x equals 4. So we're adding the y value of the f function when x equals 4, then the y value of the g function when x equals 4, and so on. So f of 4, let's look at the graph. 1, 2, 3, 4. That is negative 0.5. And the g function, that is negative 2. And the h function, this is the easiest one of the bunch because we just go to where x, remember that 4 in parentheses is an x value. We just go to where x equals 4 and we find out what the y value is. So h of 4 is negative 3. So we're going to add negative 3. So what is that? That's negative 5 plus negative 2 plus negative 3. So this is negative 5 plus another negative 0.5. So that is negative 5.5. We have to do this without the calculator. Negative 5.5 for that one. H times f of 2, remember all that means is h of 2 times f of 2. So we are looking for the value of the h function when an x goes in, or when the input is x, and the value of the f function when the input is 2. The value of the h function when x is 2, is negative 1. And the value of the f function, that is the, I'm going to label these again so I don't mess this up. The value of the f function when x equals 2, what is that? That's negative 1.5. And negative 1 times negative 1.5, of course, is 1.5, positive 1.5. In terms of c here, h of a equals negative 3, what is the value of f of a? So again, this is an output, right? This is an h of a or h of x value right here. So the a is the input, that's the x. And then this guy over here is the y, which means what I need to do now is I need to look for that negative 3, not in the first column. It's not even in the first column, or at least it's not given to us in the first column. I need to look for that negative 3 in the second column and then find out what x value in the first column produces that -3. This is one of those output to input questions. I'm given an output, I need the input. So the -3 is right there. We talked about that point before. The input that produced that output is 4, which means that A must be 4. When A is 4, this is H of 4, and H of 4 produces the -3. 4 produces -3. So I'm talking about evaluating now f of 4. I know my A is 4, so I'm doing f of 4. 1, 2, 3, 4. It's that same point we've looked at a bunch of times already, is going to be -0.5. -0.5. In item D here, h of f of 1, a composite function. So again, inside function first. I need to do f of 1. That means I need to find the y value, the value of f, at x equals 1. That's an x value. So x equals 1. The y value there on the f function is -2. And now I need to substitute that -2 in for f of 1, because I know f of 1 equals -2. So I'm looking for h of -2. I go into my table, which gives me my h values. I find out where the x value is -2, and I spit out the 5. So h of -2 equals 5. In item E here, let's take a look at item E. What is the value? So another composite function. What this means is g of h of, I'm not going to write x because they tell me x equals 2. So I'm just going to write g of h of 2. That's what all of this would mean. So again, x is 2. G, the composition of the g and h functions when x equals 2 could be written as g of h of 2. And very simple, h of 2, going to go into, again, inside function first. I'm going to write this over here. H of 2, I can see that right there. When x is 2 in the h function, and output is -1. So now all of this just becomes -1, and I have g of -1. I go on to the graph here. There's the x value of -1. Down to the g function is, that's the g and the f function. They intersect there. That's -3. So g of -1 equals -3. In item f here, for what value of x in the table is h of x equals 0 and f of x less than g of x? Ooh, okay. So again, this is an output to input question. That is a y value or output value, which means I need to look for that 0 in the right-hand column of the table where my h of x or y values are, and I need to find out what value of x will produce that 0. And what happens here is I actually have two places where h of x equals 0, one there, and the two x values that produce those zeros are -4 and 0. So what that means is that I'm talking about an x value of -4 or an x value of 0. They want to know for what value in the table is h of x equals 0 and f of x less than g of x. So I've got to look at these two values of x on the graph and find out where the y value of the f function is less than the y value on the g function. So at -4, is that true? Here is x equals -4. Is the y value on the f function less than the y value on the g function? Indeed, it is. The y value on the f function is way below the y value on the g function there, and that is what we needed to be true, which means we know it's that -4 value that's the value that we want here. When x equals 0, so that's right there, x equals 0 along the y-axis, we can see that the y value on the f function is actually greater than the y value on the g function, so that 0 does not satisfy this stipulation. If f of t equals g of t, what is one possible value of h of t minus 3? So again, all this means is we're looking for a point where these two functions, the f and the g function, intersect, where the y values are equal. That means a point of intersection. There are only 2 points of intersection between those two functions. There is one here, and there is one here. That is at x equals -1, and this one over here, 1, 2, 3, 4, 5. That is at x equals 5. So what did I say? X equals -1 and x equals 5. These are t values. Technically, I should be writing t there. Sorry. T is our x value here. So t would equal 1 or t would equal 5. They want one possible value of h of t minus 3. So I'm just going to choose the 5. It's a little bit easier. So h of 5 minus 3 t minus 3, 5 minus 3 is going to be h of 2. And again, I just go in the table to where my x value is 2, and I find out that the y value there, the value of the h function is -1. So that is one possible value of h of t minus 3. If I use the -1, that would be -1 minus 3, which is -4, and a -4, that would produce that 0 right there. So 0 was another allowable answer there. H and I, and then we will wrap this up. In terms of item H, if the function p not shown is divided by p of x equals whatever, and h of a equals p, wow, there's a lot of stuff here. Okay, so they want the value of a. So let's take a look at this. They want a place where h of a equals p of -3. So the way to start here is just to take this -3, which again is an x value, it's in parentheses, get that x into the p function for x. So let's do that. So p of -3 equals -3. I'm going to make sure I use parentheses here so I don't make any careless mistakes. -3 squared minus 3, what is that going to be? That's 9 minus 3, so that's 6. So all of this over here, p of -3, that just equals 6, which means this equation becomes h of a equals 6. Remember, this is an output to input question. We need to figure out what x value, in this case an a value, but a is an x value, produces a 6, and that has to be, there's only one place where 6 is produced as an output. It's right there. So working our way back to the input that produces that output, it must be that a equals 6. A has to be 6 because h of 6 equals 6, and that's the only place where we get a 6 as an output. Item I here, if the function a, not shown, is defined by a of 2 of x equals g, holy gajoli, that's a lot of stuff there. Let's take a look at this. This is one of those cases, I talked about this in a previous video, in a previous section, that sometimes we'll get inputs that are not simple x's. They might be an expression. In this case, we have a 2x. And we have to understand that when we're talking about a of 6, if that 6 is a 2x, that 6 is a 2x, what that means is that x must be 3. 2x is the 6, divide by 2, divide by 2. That means that we pull an x value of 3 out of that input of 6. And then once we have that 3 can just go in for all of these x's on the right-hand side of this equal sign. So we're talking about g of f of 3 minus h of, that's, I'll just do this arithmetic. 2 times 3 is 6 minus, so that's just h of 2. Let's get that h of 2 out of the way. That's the easiest one to start with. H of 2, that 2 is an x value, so that's -1. So that's minus -1. So that h of 2, we're done with that. F of 3, what is f of 3? So when x equals 3, 1, 2, 3, it looks like -1. So, all right, let me just do this one little step at a time. So that's g of -1 because f of 3 was -1. And then the g of -1, go to where x equals -1. So that's going to return a -3. So that is -3 minus -1, which is -3 plus 1, which is -2. So that guy is -2. So look, I know we just went through a ton of examples. I know it took quite a bit of time, but it is important to be very confident and very nimble with all of these different ways that College Board might decide to test functions, you know, the output to input, the way that that relates to, or the input to output, the output to input, the composite functions, where one function is greater than another function, where two functions are equal to each other, points of intersection, in other words. Very important to have a very flexible and thorough knowledge of all these different ways that College Board might throw function graphs at you.